All right, let's just dive right in. Today, we are talking about what is maybe the single most ambitious quest in the history of science, the search for one single, powerful theory that explains our entire universe. We're talking everything from the tiniest quark to the biggest supercluster of galaxies. This is the story of that hunt, the search for the theory of everything.
So when scientists talk about this, they use phrases like the greatest achievement of all time. And for good reason. Imagine a theory so complete, so perfect, that you could plug it into a computer and simulate our entire universe from scratch. This isn't just about chalk on a blackboard. We're talking about finding the literal source code of reality itself. It would be, well, the greatest achievement of all time.
So how do we even begin to wrap our heads around something this massive? Here's our roadmap for this explainer. We're going to start with the dream itself, the ultimate simulation. Then we'll look at the three main tools we have right now, the pillars of physics. That's when we hit a huge roadblock, a major paradox. But don't worry, we'll get to the elegant solution, and finally, we'll see where this incredible quest stands today.
Okay, so first up, the ultimate simulation. The goal here, the absolute dream, is to find a set of rules so fundamental that it could explain everything. And I mean everything, from how cream swirls in your coffee to the explosive, fiery birth of the cosmos in the Big Bang. It's the holy grail of physics, basically a complete instruction manual for reality. Now, to even attempt to build something like this, physicists have three incredibly powerful sets of laws. You can think of them as our fundamental toolkit for understanding the universe. But as you're about to see, these tools were never really designed to work with each other.
And here they are, the big three. You've got special relativity, which is all about space and time doing weird things to protect the cosmic speed limit. Then there's universal gravitation, the simple idea that everything pulls on everything else. And finally, you have quantum mechanics, the truly bizarre but powerful rules that run the microscopic world. For over a century, these have been our master theories.
First, let's talk about special relativity. This is Einstein's mind-bending idea that space and time aren't some fixed, rigid backdrop. Nope. It's more like a stretchy fabric that can warp and bend to make sure that one ultimate rule is never, ever broken: the speed of light. Next up, good old universal gravitation. This one feels a little more intuitive, right? It's that invisible force that holds galaxies together, keeps planets in their orbits, and, keeps your feet firmly planted on the ground. Everything with mass pulls on everything else. Simple as that.
And finally, quantum mechanics. Okay, this is where reality gets weird, like really weird. Down at the tiniest scales, nothing is solid. Everything, you, me, the screen, is actually just a wave of probabilities. It makes zero intuitive sense, but it is unbelievably successful at describing the subatomic world.
So we have these amazing frameworks. The logical next step would be to just combine them, right? Well, that's where modern physics hits a massive brick wall. This is the central problem of our story. Our best tools just flat out refuse to cooperate. So what gives? What is the actual problem here? Why can't these incredible theories just get along? The whole issue, believe it or not, boils down to how they each define the most basic building block of the universe: a single, simple particle. Okay, check this out, because here's where it gets strange. When you combine gravity and relativity, a particle's mass gets squished into an infinitely small point, which basically creates a tiny spinning black hole. But if you look at that exact same particle using quantum mechanics and relativity, it's not a point at all. It's a fuzzy, spread-out wave of possibilities. So which is it? A point or a wave? It can't be both. That's the paradox.
And the mind-bending solution that physicists eventually landed on is this. The problem isn't with the theories. The problem is with the particle itself. The very idea of a tiny little point zipping through space is the fundamental flaw. The reason the math breaks down is because, in a very real sense, particles don't exist.
Whoa, okay. So if not particles, then what in the world are we made of? This brings us to the big breakthrough, the elegant solution that finally allows our master theories to speak the same language. It's an idea that gets rid of points and replaces them with something much more fundamental.
And here's the answer: the unified field. The idea is that reality isn't made of tiny billiard balls. It's made of continuous, vibrating fields that stretch across all of space and time. And what we call a particle, like an electron, is really just a concentrated little vibration, a ripple, in the larger electron field. This one shift in thinking solves the entire paradox.
And what's so beautiful is how this one idea just clicks everything into place.
The field itself explains the wave nature of quantum mechanics. Check. A ripple in that field traveling at light speed explains relativity's cause and effect. Check. And the way these fields bend space-time explains gravity. Check. One single concept elegantly explains all three pillars.
So, a universe of fields is the answer. Case closed, right? Well, almost. We figured out the type of answer we're looking for, which is a massive step. But now we're face to face with a final monumental challenge: finding the one specific theory, the one master equation that actually describes our reality.
And this is the last big hurdle. The whole concept of a unified field is so powerful and so promising that physicists have actually come up with multiple different versions of the theory. So the scientific community is now in this amazing race to test and debate which one is the correct one.
Right now, the search has basically narrowed down to two incredibly successful frameworks, called the two standard models. First is the Standard Model of Particle Physics, a quantum field theory that describes every known particle and force, except gravity, with stunning precision. The second is the Standard Model of Cosmology, which uses Einstein's geometric field theory to describe the entire evolution of the universe. The final, ultimate challenge is to unite these two into one.
And that leaves us right here, with this thrilling question that physicists are working on at this very moment. We have the framework, we have the tools, we are closer than we have ever been before. But that ultimate prize, the one true theory of everything, is still just out of reach, waiting to be discovered. Which theory will it turn out to be?